In the first part of the video, we studied the rheological properties of the solids. We learned about what the stress, strain, Young's modulus, and Poisson's ratio is. Let's try to solve a couple of problems to understand the concepts better. So, there are fibers, semolina fibers, okay. So you basically take the fiber and you are going to stress it out, okay. So you hold it and then pull it out. The original diameter was 1.65 millimeters. And the fiber length is 150 millimeters. And then when they do that, the strain, if you remember what the strain is, delta L by L, and stress is nothing but the force applied per unit area, right? So, as you remember, the stress is proportional to strain, and the proportionality constant is the Young's modulus. Therefore, the slope is the Young's modulus. So if you look at the slope, it goes from 0, so you can take this value. This is 20, this is 0.004. Therefore, the stress equal to 20 megapascals divided by 0.004 should be equal to 5000 megapascals. So that is the first answer. Okay, let's go back to the questions. The next question is, what is the Poisson's ratio if the force exhibit a diameter change of 2.43 into 10 power minus 3 millimeter under a stress of 15 megapascal. So at stress of 15 megapascals, the value of the strain when stress equal to 15 megapascals, strain equals 0.003, no units, it's a unitless. And then they are saying that that's nothing but delta L over L, right? That's the axial strain. The lateral strain is delta D by D, which is nothing but 2.43 into 10 power minus 3 divided by the diameter, which is nothing but 1.65. Then the Poisson's ratio is lateral strain by axial strain. Let's look it up. So again, that's the 0.003. Mu is equal to delta D by D divided by the axial strain, which is 0.49. This is close to the value of the 0.5, meaning that porosity is almost close to 0. Okay. So by doing an experiment and collecting a FD curve, force deformation curve, or a stress strain curve, you can determine the properties like E and mu, Poisson's ratio. This you will be doing in the lab on Tuesday and Thursday. So let's look at another example problem. Okay. An apple cube, so it is a cube, so let's take a cube of a side of 20 millimeters and is subjected to the uniaxial compression force of 28 newtons. It's distributed over two opposite faces of the cube. Well, when you basically apply a force on one direction, there is a normal force always act, right? There is a normal force act upwards, right? So that's the ground reaction force. So that's why it's called as the on both sides. So you can just take it as F is equal to 98 newtons. And assume the apple has an apparent modulus of elasticity of 5.15 megapascals and Poisson's ratio of 0.23. So you know the material property. So what do they want to know? They want to know the dimensions of the deformed cube. So basically, if you can know what is delta L, or let's call it as delta H. Let's call it as a delta H and maybe delta B. Those are the two things you need, so that you can determine the new H, new B prime, which is again the L prime. Okay. So those are the things needs to be found. So you know the force, you know the area, right? So the area is 20 by 20, 400 millimeter square, right? Let's go to the next one. So the first step is to calculate stress. Stress equal to force per unit area. The forces, so let's look at again. Stress equal to force per unit area. The force is equal to 98 Newton divided by, if I want to convert it to meter square, is equal to 0.245 megapascals or 10 power 6. Let's go step at a time. Times 10 power 6 pascals or 0.245 megapascals. The modulus of elasticity is given as 5.15 megapascals, which is equal to stress over strain, right? That is an axial strain. Therefore, axial strain is equal to stress over Young's modulus, which is equal to 0.245 divided by 5.15, which is equal to 0.04757. Okay. So the axial strain is the change in height over the original height equal to 0.04757, which is equal to delta H over 20 millimeters. Therefore, delta H equals 0.95 millimeters. Right? Then the Poisson's ratio is the lateral strain over the axial strain, and the Poisson's ratio is given as 0.23 is equal to the lateral strain over the axial strain is 0.04757. Therefore, the lateral strain is equal to 0.23 times 0.04757 should be equal to 0.01094. Okay, so lateral strain is equal to delta L by L, it's on the lateral direction, is equal to delta L by 20 is equal to 0.0194. Therefore, delta L equal to 0.22 millimeter. So the new height is equal to equals original height minus delta H, right? Because it's compression. So that is equal to 19.05 millimeter. The new length is equal to the length plus delta L, which is equal to 20.22 millimeter. Because the breadth direction is the same, so you should get the same dimension. So the dimensions of the deformed cube will be 20.22 by 20.22 by 19.05 millimeters.